Hi, thank you very much for coming by. My poster is discussing verification work that we have performed recently between Broadband CyberShake and the SCEC Broadband platform. And so this work is important because the two platforms use different codes to do their low frequency calculations. And you can see that reflected here in these two workflows, that all the green codes here are the ones that the Broadband platform uses. Broadband CyberShake uses, the same codes to calculate site response and do the filtering, do the high frequency, but different codes when it comes to the low frequency components. And so we want to compare these results and see if we get good agreement. Because if we get good agreement, that gives us a lot of confidence in that both simulations are working correctly. We don't expect them to match exactly, but we did want to be able to explain why we see differences that we see. And so in order to do this, the first thing we did was perform a fairly involved set of initial tests to take a look at differences that we might see and be able to explain them. So for example, one thing we found is that there is a small time offset, and it turned out that that's because the two grids put the stress and the velocity elements in different spots in the grid. So you end up being, for example, half a grid point off. And so, that's one example of something that we found. Another element that we discovered is that the velocity model that's represented in the Broadband platform needs to be modified slightly so that the finite difference code that we use in CyberShake ends up, seeing, as it were, an equivalent velocity model. So we discovered we needed to add these additional transitional layers to get to something equivalent. We also found that our typical grid spacing of 100 meters in CyberShake, we start to run into resolution issues when we look at kind of 1 hertz and higher. And so we discovered that, just kind of as a test, if we go to more refined grid spacing, our results start to converge towards the frequency wave number solution that's used in the Broadband platform. And so that, gave us a lot of confidence that both of these are converging towards the same results, and also encourages us moving forward. We're thinking about next steps for CyberShake. Maybe we should integrate the discontinuous mesh code, which enables us to have this more refined grid spacing at the surface, where it's important to be able to resolve some of these higher frequencies. Once we finished that, the next thing that we did is move to a more complex set of verification work. So we selected the Northridge event from the Broadband platform. I want to be clear here that these comparisons I'm presenting today are all simulation to simulation. We haven't yet gotten to the point of using observations, though obviously that's coming up in the future, and that's where we're going. We just haven't gotten there yet. So here what we did is we ran 1D simulations for Northridge. We selected the 10 stations I have outlined here and ran them on both platforms and then compared the results. And so I'll go ahead here and show you a couple of sets of the traces. Let me zoom in a little further so it's easier to see. So for instance, for this site, SCE, which is practically on top of a fault, you see pretty good agreement in the velocity seismograms. The FAS is very close. The PSA has a small difference here at 1 second, but otherwise looks pretty good. Other sites show similar trends. We see actually here really good agreement in PEL, which is I think 10 or 15 kilometers away. And then down here at FEA, which is about 45 kilometers away, we start to see a little bit of divergence. This isn't too surprising. And overall, we're pleased with the level of agreement, especially here in PSA. To get a sense of overall, how have we done? How do the 10 stations compare? These are some goodness of fit results. So here what we've done is we've plotted Broadband divided by CyberShake at different periods. We see a little bit of divergence at large distances at longer periods. And this makes sense. This is likely due to both that the way the Broadband platform discretizes things at large distances, and also that the modifications we made to the velocity model, may have a slight impact at large distances that we see here. Overall, though, the goodness of fit looks very good. You can see kind of the mean is very close to 0, and the confidence intervals are quite symmetric. And so overall, we're very pleased with these results. We're ready to move forward with the future comparisons. So we're going to look at different events. We're going to look at more stations. And then ultimately, we're going to take a look at real observations and start validation work. Well, thank you very much for stopping by. And please, let me know, either send me an email or post if you have any questions.